So in this video we'll discuss about two hinge arch, okay, and consider a two hinge arch. Okay, you can see two hinged arch of a span L and a crown height H, and basically it is a indeterminate structure, okay, of degree of indeterminacy 1. Okay, two vertical reaction will be acting at end A and B, and horizontal thrust will be acting on either side. Here we consider a arch equivalent to a simply supported beam. So the basic concept here is, okay, for a simply supported beam, okay, moment in I'm writing in shortcut, okay, simply supported beam SSB. Moment in simply supported beam is equal to, if it is MSS, then moment in arch is equal to moment in simply supported beam minus H into Y, that is horizontal thrust multiplied by the vertical distance. So this is the working procedure of arch and how it is efficient than the simply supported beam. Also, if I is the moment of inertia at any section, which is given by IC into sec theta, where IC is the moment of inertia at crown and sec theta being dependent on the theta. The formula for horizontal thrust is given by this expression: moment in simply supported y dx by EIC divided by 0 to L y square dx by EIC. So this is the expression for horizontal thrust. And okay, so this being arch and the thickness at the central portion T, a simply supported beam of thickness T is considered, and further calculation is done with the assumption of relation between a simply supported beam and a two hinge arch. Okay, so this is how two hinge arch are solved. Now going into a numerical now. So in this question, a two hinged parabolic arch is provided with the right portion being loaded with a UDL of 10 kilonewton per meter and a point load of 20 kilonewton at 10 meter from the left support as shown in the figure, and we are asked to find horizontal thrust, bending moment, normal thrust and radial thrust at a section 30 meter from left. Okay, so at point E we are asked to find the various parameters. So now let me write this step how to solve this problem, okay, or the problem related to hinge arch. The very first step is we are going to deal with the horizontal thrust, and for which the formula is MSS, that is moment in the simply supported beam portion, y dx by EIC divided by y square dx by EIC. Okay, so we have to find out the moment throughout the portion of the simply supported beam. Okay, and we will construct a moment table, for which we will do in the numerical directly. Starting with, as I have already said, the arch is compared to a simply supported beam. So now we will draw the simply supported beam for this arch. Okay, consider a simply supported beam of span 120 meter with mid span 60 meter, that is C, and a point load is acting at a 10 meter distance from left support, and the magnitude of point load is 20 kilonewton, and UDL is applied throughout the right portion, throughout the right half portion of intensity 10 kilonewton per meter. Now here we will find the reaction at A and B. Okay, So applying the static equilibrium condition, we can find out the reaction taking moment about A as 0. Okay. RB gives anti-clockwise, 10, 20 gives a clockwise, so 20 multiplied by 10. This also gives a clockwise, 10 multiplied by the distance is 60 meter, acts at the center. So this being 60, 30 plus remaining distance as it is acting at this point. So 30 plus 60 minus RB gives anti-clockwise, so RB multiplied by the whole span 120 is equal to 0. So RB is equal to 20 multiplied by 10 plus 10 multiplied by 60 multiplied by 30 plus 60 divided by 120. We get 451.667. 451.667 kilonewton upward. Okay. Similarly, summation Fy is equal to 0, taking upward positive, minus 20 minus 10 into 60 plus RB plus RA. So RA is equal to 2600, 451.667. So we get 168.35 kilonewton acting vertically upward. So this is the first step, that is calculation of reaction for simply supported beam. Okay. So RA is equal to 168.35 and RB is equal to 451.667. The next step is to calculate horizontal thrust. Okay, to calculate horizontal thrust, and the formula is m dx, that is mss, okay, y dx by eic divided by y square dx by eic. Okay, so we'll have to find the horizontal thrust, for which let me start with the denominator term. Okay, so in this we have y unknown. So for y, as it is a parabolic arch, so y is equal to 4hx by l square l minus x, h being the height at the crown, x being the section distance, l being the span. Okay, so make sure you remember we are taking a distance at a section from the support. Okay, from a support, say x distance. Okay, and this will be important while calculating the moment from the table. So let me make you clear about this term. Okay, so we take a section from the support, and in this case h being 20. Okay, so this is 20. So 4 multiplied by 20 into x, 120 minus x divided by 120 square. So we get on dividing, we get 4 multiplied by 20 divided by 120 square, we get 0.0055 x 120 minus x. Okay, so this is the value for y. Now for the upper term, that is for numerator, let me draw a moment table. Okay, moment table. So the very first row is for the member, then we have limit, and finally the moment MSS. Okay, if we start with the left support, that is member AD. Okay, then we have DC, and then finally CB. I'll consider the origin A. Okay, because we are taking a section from the support, so A. For DC, again we'll consider the left support, so origin as A. Okay, and for BC we can consider the support at B. We can consider at C also, but it will be vague because we have to consider so many moments from the previous portion. So we'll consider B as the origin. Limit for AD, it is 0 to 10. Now for DC, we are considering only DC, so 10 to 60 because the previous 10 meter is already considered, and for BC it is again 0 to 60. Now we have to determine the moment at the member. So from A to D, 168.3, that is the reaction at A, will be acting at a distance. If we consider a section of x meter, then 168.3 x clockwise, so positive. Okay, then 168.3, this x now reaches to this point, so this total distance being x, okay, 20 kilonewton meter, 20 kilonewton only. Okay, so at a section x, 168.3 will be giving the same, that is multiplied by x minus 20 kilonewton anti-clockwise, so minus 20, this distance being, okay, this distance being x minus 10, because this whole portion is x and this from A to D it is 10, so 20 x minus 10. And finally for CB, it is, we are moving from right to left, and from right to left anti-clockwise is positive, so 451.667 at a sectional distance x minus, this will give a clockwise moment, okay, this radial, so minus 10 into x divided by 2. Okay, so this is the moment table. Remember, you will be considering a sectional distance from the support, so you can't start with the origin at the mid span, this being the moment table. Now we substitute the value of MSS y in the equation. S is equal to MSS y dx divided by EIC divided by y square dx by EIC. So at first let me determine the numerator. So MSS y dx by EIC, okay, which is equal to, now we'll consider the value for each member separately. So 168.3 multiply by this, because MSS into y, and the span being 0 to 10, okay, for the numerator. MSS for AD portion is 168.3x, so 168.3x multiply by y, that is 0.0055x, 120 minus x dx by EIC. So for the next portion we have and finally we have for CB, which is 451.667x minus 10 divided by 2, so it will be 5x square, okay, and similarly for y it is 0.0055x, so 120 minus x divided by EIC. So while writing the limit, make sure for the numerator part you have to write member wise, okay, 0 to 10, 10 to 60, and this for this 0 to 60. But in case of the numerator term in this equation, okay, y square dx by EIC, the limit is 0 to 120, that the span of the whole arch, okay. So with this, what we inserting this value in calculator, we can calculate the numerator part. So 168.3x multiplied by 0.0055 x, 120 minus x, okay, limit 0 to 10 plus this equation now, 168.3 x minus 20 x minus 10 multiply by 0.0055 x 120 minus x, okay, limit being 10 to 60, and 451.667 x minus 5x square 0.0055 x 120 minus x, and the distance being 0 to 60, we get value as 1 by EIC is common, okay, 1 by EIC is common, so the value being 1156011.57. so this is the value for the numerator part, okay. So now horizontal thrust is equal to, so we have calculated the numerator part, that is 1156011.57 by EIC. For the numerator part, so now y square, and it will be from throughout this span, so 120 y square, that is 0.0055 x 120 minus x to power square, okay. One 11560.111.57 divided by integration from, that is for 0 to 0055 x 120 minus x to power square divided from 0 to 120, okay. So it is 460.73, 460.73, okay. We have EIC here also, it will cancel out, so 460.73 kilonewton, okay. This is the horizontal thrust. For normal thrust, bending moment, and radial shear, okay. For bending moment at 30 meter from left, that is at point E, okay. So for which we have to find some terms, which is y is equal to, as we know, 4hx divided by l square, l minus x, we know the value for h, that is 20, x being 30 meter, l square, that is 120 to power square, l 120 minus 30, so we get the value y as 4 multiplied by 20 multiplied by 30 divided by 120 square multiplied by 120 minus 30, so this being 15 meter, okay. Okay, tan theta is equal to dy to dx, and the derivative of this, we get 4h divided by l square, l minus 2x, and finally theta is equal to 18.43 degree, okay. Theta is equal to 18.43 degree. Now for bending moment at 30 meter, consider a section, okay. We have the horizontal thrust and vertical reaction at point A, which is vertical we had calculated as 168.3, horizontal we have calculated just now as 460.73, and a point load is acting at this point at a distance of 10 meter, okay, 20 kilonewton. So this is the section, 30 meter total, okay, 30 meter. We can calculate the bending moment at E. So bending moment at E is equal to 168.3 multiplied by this distance 30 meter, it is a sagging moment, so positive, minus 460.73 negative, okay, multiply by this height we have just calculated as 15 meter, multiply by 15, and this gives a anti-clockwise again, so minus 20 multiply by this distance 10 30, so 30 minus 10 20, so the moment here is minus 2261.95 kilonewton meter. Okay, so this is the moment at point E. So now we have to calculate the radial shear and normal thrust at section E. For normal thrust at 30 meter and radial thrust, okay. So at point E, a normal force acts, okay, which is known as normal thrust, and perpendicular to normal thrust, another force acts, that is radial thrust, making an angle theta with the horizontal. We had calculated theta as 18.54. We had 18.435 degree, and y at that section 15 meter. Okay, so resolving normal thrust, if we see, theta, okay, resolving a vertical force acts here, is it 20 kilonewton acting downward and 168 acting upward. So to balance this, an extra force has to be acted in the downward direction, so which is equal to 168.3 minus 20, that is 148.3. V is equal to 148.3 downward, so we'll take positive because radial thrust is also acting downward and this also acting downward, so it is taken as positive. Horizontal, that is H, 460.73. Now the formula for normal thrust, if we resolve this normal thrust and this radial thrust in terms of horizontal and vertical, okay, normal thrust is equal to H cos theta, okay, if we resolve in terms of normal thrust, as cos theta plus V, okay, this being V, making an angle sine, okay, V sine theta. Substitute the value of V and H and theta 460.73 cos 18.435 degree plus 148.3 sine 18.43. 460.73 cos 18.435 plus 148.3 sine 18.43. So it is 483.97 kilonewton. And for radial thrust, if we see, this acting downward, this is acting downward, so it is positive. So now this being theta, this angle becomes theta, so radial thrust makes V cos theta, okay, acting in same direction. And if we resolve this in terms of horizontal, it acts in this direction, and horizontal acting in opposite direction, so minus H sine theta. Okay, substitute the value for V, that is 148.3 cos 18.435 minus H being 460.73 sine 18.435, we get minus 5 kilonewton. If we are provided yielding of support, then we have to consider in the horizontal thrust. Okay. So in case if you are provided with some yielding at support, rib shortening effect, temperature effect, then it has to be considered in the horizontal part, horizontal thrust calculation. Okay, for example, if you are provided with the yielding at support, okay, for example, it is said that if support B yields by 10 mm, okay, then it means you have to subtract here with the yielding value, that is delta. Okay, if it is 10 mm, then you have to write minus 10 divided by 1000, you have to take into meter. So okay, for example, if the support B yields by 10 mm, then minus 10 divided by 1000. Okay, in case if both the support yield, then you have to make a, if the support A and B yield by delta 1 and delta 2 respectively, then delta 1 plus delta 2 will be the effective yield. Okay,